Today we're going to talk about where power series come from and why we care about power series. The first place we're going to look is we're going to look at Taylor series. We're going to look at how to build a Taylor series. The good news is y'all have started on the Taylor series path because back in Calc 1, you went and found the equation of a tangent line. A Taylor series is just like a tangent line where you keep going. You don't stop at degree 1, you just keep on going. So a Taylor series is a power series based on a function. We can also build a power series from a description, like a differential equation. I usually do an example of taking a differential equation and writing, assuming that a power series solution, and then just making some calculations to come up with the power series. This is not something that anyone should ever do, ever, but it's fun to do because we take this generic description of a function and generate a power series description for it. That's something we could ask machines to do. So we care because Burrels theorem, I didn't label this as Burrels theorem. Burrels theorem implies that every power series is the Taylor series of some smooth function. So every time we've looked at some power series, even those weirdo examples that I came up with to practice finding the interval of convergence, that's the Taylor series of some function. This is Burrell's theorem. It's Burrell, right? It is for now until I correct myself. So Burrell's theorem gives us that all these power series that we're looking at, they're Taylor series of some smooth function. So there's some connection between these functions that we're familiar with and these power series that we've been looking at. So let's look at Taylor series. We'll start by looking at Taylor polynomials. And this will become Taylor series because we just keep going. Remember our thinking about what a power series was. A power series is just a function in the form of an infinitely long polynomial. It ceases to be a polynomial once it goes on forever. But we write a Taylor polynomial and we turn it into series by writing plus dot dot dot. So just keep going with whatever was happening here. So let's do an old problem. Let's find the equation of the line tangent to f of x equals e to the x at x equals 0. One of our more important power series. Let's start with a tangent line. Let's find the equation of the line tangent to f of x equals e to the x at the point where x equals 0. So, old school Calc 1 skill. So, harken back to the halcyon days of Calculus 1, where things were so simple before they got all complicated with this integration business. What we need to know is we need the equation of a line. That means we need a point and a slope. Those are the ingredients we need to make the equation of a line. So we need a point. The point is just when x is equal to 0, and I need to figure out what the y coordinate is. So if x equals 0, f of 0 is equal to e to the 0, which is equal to 1. So our point sorted. We got a point. Now we need the slope, and calculus says the slope of the tangent line will be given by the derivative. So we need to find the derivative. So the derivative of f of x, f prime of x, is e to the x, and the slope will be the derivative evaluated at 0. Which is also going to be 1. So the equation of the tangent line, we start off at 1, and we increase by 1 every x. So here's what we care about the tangent line. The value of the tangent line and the values of the tangent line at 0 match those of the function. That's what's going on. So the tangent line let's say y of x, the tangent line agrees with the function at 0 in value and first derivative. So y of 0 is equal to 1 plus 0, which is equal to 1, and y prime of x is 1. So y prime of 0 is equal to 1. So the values of the derivatives of the tangent line are equal to those of the function. The tangent line, I don't know why this had to be in red, so emphasis. The values of the function and the tangent line agree at all the derivatives. So we build the tangent line by matching the value of the function and the value of derivative. The tangent line is a line with the same value and first derivative. So the tangent line is the line with the same value and first derivative of the first derivative when x equals 0 as the function when x equals 0. I don't know if this is a more coffee problem or a less coffee problem, but I'm clearly having trouble with sentences today. So what we want to do with this idea is to just keep going. Let's, instead of build the equation of the line tangent to the function, let's build a quadratic approximation of the function, the tangent quadratic. Can we build a tangent quadratic? Can we build a tangent quadratic? Can we build a quadratic function, q of x, centered around 0, so let's say c plus bx plus ax squared, to the function at x equals 0. So what we want is we want the value of q of x and the value of f of x to agree at 0 in all their derivatives. So if I look at the values of the function, so the function is f of x. This e to the x is bothering me. No, I'm just going to let it bother me. So f of x is e to the x because all the values are the same, and I'm doing a very Hughes Howlett move. And I want it to agree at the first derivative and the second derivative. I'm switching functions in the next example anyway, so. And we want to look at the value of the function at 0 and all of its derivatives at 0, and these are all going to be 1. Now I want to look at the values of, I want to look at q of x, and I want to figure out the values of a, b, and c, so that when I take the derivatives, it will be all the same as the derivatives of the function. So q of x is going to be c plus bx plus ax squared. Q prime of x, the c drops out, we get b plus 2ax, and q double prime of x is just going to be 2a. Now, when I evaluate the function q, the quadratic, at 0, and all of its derivatives at 0, I want them to equal the values of the function. So q of 0 is equal to c. Q prime of 0 is equal to b. Q double prime of 0 is equal to 2a. And what I want is that the values of the quadratic function at 0 to match those of the function at 0. I want f of 0 to equal q of 0. That is, I want 1 to equal c. I want f prime of 0 to equal q prime of 0. That is, I want 1 to equal b. And f double prime of 0 needs to equal q double prime of 0. So 1 is equal to 2a. So a is equal to a half. So the tangent quadratic to e to the x at x equals 0 is going to be 1 plus x plus 1x plus a half x squared. Now we can look at this in our graphing calculator. So let's switch over to the graphing calculator. So here's our function e to the x. And if we look at y equals 1, this is just the value of the function at 1. This is the best 0-degree approximation of e to the x when x is 0. Just the value of the function. That's kind of crazy to stop there. So, So we build the tangent line. The tangent line is the best linear approximation to e to the x near x equals 0. If we zoom in close, if we zoom in real close, we can see that there's very little difference between the functions. If I keep it really close, I can say, look, they're the same. This is the same way that people stand in a flat field and say, ah, the entire Earth must be flat, but they just need to zoom out and realize that they're wrong. So all we're doing is we're taking our tangent line and adding more terms to it. So if I add a half x squared, now I get a tangent quadratic. I get a parabola that approximates the function e to the x. And if I zoom in, we can see that this parabola is very close to the function e to the x as long as we stay near x equals 0. So this raises an important question. Why stop at second degree? Oops, that's not what I wanted. This raises an important question. Why stop at second degree? Can we build a tangent cubic? Can we build a tangent cubic? What if I want a function that's not I want a cubic function. I'll call, I can't use C. I use K for mortal cubic. Can we build a cubic function, C plus BX plus AX squared, and then add another term onto it, like say DX cubed? That will agree with the function f of x. So we can do the same thing. We take derivatives. What color did I make those? We take derivatives. So k of x is c plus b plus ax squared plus dx cubed. I just tack this onto q of x. I'm just tacking a cubic term onto it. I should have probably counted the other way, but I didn't, so we're stuck with it now. But k prime of x will be c. K double prime of x, or sorry, c plus bx, plus b plus 2ax to the first plus 3dx squared. Second derivative, the c drops out. The c should have dropped out in the first derivative. I don't know if this is a more oh, here's what I did. I rewrote the function up here, and then I just kind of combined the two things. I'm saying, why did I do that? And then I decided to switch, but the message didn't get all the way through my brain, so I don't want that c there. Are we okay now? Far from it, but we're going to keep going. So the derivative is going to be b plus 2ax plus 3dx squared. So the second derivative will be, the b drops out, and we'll have 2a plus 6dx. The third derivative will be just 6d. Our derivatives of f are the same as we had before. F prime of x is still e to the x. F double prime of x is e to the x. F triple prime of x is e to the x. The values of the function at 0 are all 1. Probably I decided to do this because I knew I wouldn't be able to evaluate a fancier function. So I picked something that would always be the same. And I need the values of my cubic function at 0. And they're just going to be the constant terms. So k of 0 is going to be c. K prime of 0 is going to be b. K double prime of 0 is going to be 2a. K triple prime of 0 is going to be 6d. And at this point, for those of you wondering where factorials came from, you should start recognizing why factorials made the convenient appearance right here. It's kind of like a video game. Video games tend to give you the object that you need to progress right before you need to move on. That's just kind of like structure. So like the NPC is like, oh, hey, I found this thing. And then you get into the dungeon and you're like, oh man, it's a good thing we had this thing. You know what I mean? So we do the same thing that we did last time. I want the values of my cubic and all of its derivatives at 0 to be the same as those of the function and all of its derivatives at 0. Notice that C, B, and A are all going to be the same as we had before. C is equal to 1. B is equal to 1. A is equal to 1/2. And the new one that we get is that 6D should equal 1. That's from 6D must equal 1 as well. And that tells us that D is equal to 1/6. So the function that we're looking for, the cubic that matches, will look like 1 plus 1x plus 1/2 x squared. Notice that if we stop at the first degree, we get the tangent line. Second degree, we get the tangent quadratic that we had before. And now we're just adding this extra term, 1/6 x to the third. This will be a cubic approximation to e to the x near x equals 0. Let's switch over to our graphing calculator and add our newly found term. So I'm going to add 1/6 x to the third. So what we're doing is we're building this polynomial, and the more terms we add to this polynomial, the closer the polynomial gets to e to the x. And you'll also notice it matches on a wider interval. So the tangent line starts to pull away from e to the x pretty close to 0. But the quadratic stays close to e to the x on a little bit wider interval. And if I throw the cubic in there, that cubic is going to be closer to e to the x on a wider interval. So tangent line, tangent quadratic, tangent cubic. The values of the cubic are closer to e to the x on a wider interval. They all match exactly when x equals 0. They're all matching at 0, 1. But then the approximation starts to pull away. More terms gets this closer on a wider interval. So I brought up factorials. And we got x squared over 2, which is 2 factorial, x cubed over 6, which is 3 factorial. We can see by how we're constructing things that the next one should probably be 4 factorial, which is 24. And notice that this function is even closer to the function e to the x, and it works on a wider interval. The cubic approximation starts to pull away. The quartic approximation stays close to the function on a wider interval. There we go. Here I even have to zoom out to see that if I look at the 5th degree Taylor polynomial approximation near 0, look how close they match. And look how far away from 0 we can get where they're still indistinguishable compared to, say, the tangent line approximation. Compared to the tangent line approximation, where we can see just even at this range how far apart they get. So this is only a good approximation at this range between, say, -1/10 and 1/10. Whereas our 5th degree approximation works all the way out from -1 to 1. Yeah, it's still working at 1. Any questions? So, good news. Taylor polynomials, Taylor series, is something that you're already familiar with. We build a Taylor series by matching derivatives. That's the big idea. We build a Taylor series by matching derivatives at a point. We build Taylor series by matching derivatives at a point. We build Taylor polynomials and Taylor series by matching derivatives at a point. So if you want the quick explanation of how to build a Taylor polynomial, that's not technical, the brief history of time style description, you're building a Taylor polynomial by matching derivatives at a point, just like a Taylor line, just like a tangent line, but keep going. Some of you are thinking, is there some formula for this? At which point, of course there is, because I wouldn't have brought it up otherwise. You know how I feel about formulas. But this one makes sense. I like this one. So the Taylor polynomial of degree n approximating the smooth function f of x near x equals a is given by. So if I recall correctly, the Hughes-Hallett calculus book calls the Taylor polynomial P sub n. My habit is to call the Taylor polynomial T sub n. I don't know where I picked this up. So t sub n of x is going to be the sum as I goes from 0 to n. The coefficients of this power series, or this is going to be a polynomial, is going to be the ith derivative evaluated at a divided by I factorial times x minus a to the I power. This is what it looks like in summation. As terms, the first term will just be f at a. The next term will be f prime at a times x minus a. These first two terms form the tangent line. The next term is the second derivative at a divided by 2 factorial times x minus a squared. And then you keep going. Third derivative over 3 factorial, fourth derivative over 4 factorial, until you get to where you want to stop. The nth derivative evaluated at a over n factorial times x minus a to the n. The x minus a to the n part, that's all just building the power series. What we're concerned with is how to construct the coefficients. It's the nth derivative evaluated at a divided by n factorial. This is just expanding on the concept of the tangent line, because the first two terms are the tangent line. The tangent line in kind of a point-slope form rather than slope-intercept form is because point-slope form is better. I don't understand this whole obsession with slope-intercept form. What if we want to start somewhere other than 0? Make our algebra students do all kind of shenanigans because we want to model something over time, but we can't just plug in the year. We can't use 1998 as a variable. So we say, well, the number of years since 1990. So 1990 corresponds to 0. All we're doing when we do that is saying x minus 1990. That's how we zero out that term. That's what makes 1990 0. You know what I mean? To make a Taylor polynomial into a Taylor series, just let n go to infinity. Instead of stopping at n, if n goes to infinity, we get a Taylor series. The point is, we build Taylor polynomials or Taylor series by matching derivatives at a point. And we've learned our first important Taylor series to remember. E to the x is the series as n goes from 0 to infinity of x to the n over n factorial. That's 1 plus x squared over 2 factorial, x cubed over 3 factorial, and so on. We're looking at a power series. And one of the things, what we're concerned with when we're looking at a power series is the interval of convergence. The center is 0, and the x to the n suggests a radius of convergence of 1, but this n factorial in the denominator that is unchecked by any factorials in the numerator suggests that the interval of convergence for this power series is all real numbers. Which is the case. So the interval of convergence for e to the x, the Taylor series e to the x to the n over n factorial is all real numbers. So that means we can use this Taylor series as an approximation of e to the x. So we can build a polynomial that approximates e to the x near x equals 0 for any real number. If we need, depending on how much accuracy we need, we can get more terms, will get us closer and on a wider interval, allow us to use this farther away from 0. But it's an approximation near 0. All right. That's going to do it for today. The next 2 Taylor series that you should check out are, say, cosine x near 0 and sine x near 0. And then, if you're feeling really fancy, the binomial series, 1 plus x to the p near 0. All right. That's it for today. Let's scroll up to the most important part. We build Taylor polynomials and Taylor series by matching derivatives at a point. We are approximating a function near a point with an nth degree polynomial or a power series. That's going to do it. If you want to read more about this, this is all in chapter 10. So check out chapter 10 on the old canvas. That's going to do it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.